Hello guys, I hope all of you are doing good. So today's lecture is about linear regression with multiple regressors. So we are basically expanding our analysis a little bit from a single regressor to multiple regressors, and the core of this lecture revolves around the concepts of omitted variable bias and multicollinearity. Alright, so the outline or the checklist for this lecture is as follows. So we will be covering the concept of omitted variable bias. We will be looking at causality and regression analysis. We will be looking at how the multiple regression model follows the OLS assumptions. We will also be looking at some of the new measures of fit which arise when we are doing regression with multiple regressors. And finally, we will be looking at the sampling distribution of the OLS estimator along with the multicollinearity problem. So omitted variable bias is the central theme around why we will actually be looking to expand the list of regressors from one to more than one. So why we will be doing that is that the error term u, which basically includes all the other variables which are unaccounted for in the single regressor model, and all of those variables which are included in the u actually have an impact on the y, the dependent variables. So what you can think of those variables are you can think of them as omitted variables. So these variables should ideally be included in the regression because obviously they have an effect on the y variable, but since they are not included, they are called omitted variables. And obviously the omission of these variables will lead to a bias in the OLS estimator, and that is what we define as the omitted variable bias. So the bias in the OLS estimator that occurs as a result of an omitted variable is called omitted variable bias. That is pretty much the standard definition for omitted variable bias. But for a variable to be categorized as causing the omitted variable bias, two conditions need to be satisfied. So first of all, we are considering the variable z as a possibly omitted variable. So we will think of z as whether z is following the two conditions for omitted variable bias, and the two conditions are as follows. So number one, the condition number one is that z is a determinant of y. And now that is pretty simple to understand and also very important, and simply because if the variable that you're considering to be an omitted variable does not have any impact on the y variable, the dependent variable, it means that this variable should not be included in the regression because it does not have first of all, it does not have an impact on the dependent variable, so it doesn't make any practical sense to include this. And secondly, it does not follow one of the two conditions for omitted variable bias. Now, what is the second condition? The second condition is that z is correlated with the regressor x. Now, if that is the case, now z is part of u. If that is the case, if this condition is actually true, then it would mean that the correlation between x and u is not equal to 0. And when that is the case, it would mean that our first assumption of the OLS model is not being satisfied. And whenever any of the assumptions of the OLS model is not being satisfied, it means that your regressor would not be the best possible regressor. It would essentially mean that that the estimator of the regressor will not be the best possible regressor. So these are the two conditions which need to be satisfied for a variable to be thought of as causing omitted variable bias, and we will look at both of these with the help of a practical example in the next slide. Now take the example that we were using in the previous lecture, that student-teacher ratios have an impact on students' test scores. Now over here in this analysis, student-teacher ratio is the X variable and student test scores is the Y variable. In this example, the English language ability will possibly have an effect on the standardized test scores. Now, why is that the case? It's simply because since the tests are conducted in English language, if you have a higher ability of English language, it should theoretically have an impact on your test scores. So another important thing to note about this observation about having a higher English language ability can lead to better test scores is that immigrant communities tend to be less affluent and thus have smaller school budgets, which means that they will possibly have higher student-teacher ratios. So what are the two conditions of omitted variable bias? The first condition is that the omitted variable should have an impact on the dependent variable, and in this situation the English language ability of the student will have an impact on the test scores, which would mean that the first condition of omitted variable bias would be present or would be satisfied. Now, if the second condition, if the second point on the slide is also true, that immigrant communities tend to be less affluent, which would result in smaller school budgets and ultimately higher student-teacher ratios, it would mean that the correlation between student-teacher ratio and English language ability is not actually zero, which would once again mean that the second condition of omitted variable bias is satisfied. And so if both of these conditions are being satisfied in this situation, then it would mean that controlling for English language ability, or in simpler terms, including English language ability as one of the regressors, would be a better outcome, because removing that or not including that is actually leading to omitted variable bias. Now, what would be the direction of this bias? So what does common sense suggest? So simply look at the relationship which are involved in both of these conditions of omitted variable bias. Now, how will English language ability and student test scores be related? So they will be related positively, because if the student has higher English language ability, it should technically lead to higher student test scores. On the other hand, let's also look at the relationship between student-teacher ratio and English language ability. Now, if the English language ability of students is higher, it should mean that the student-teacher ratio should be lower. So in this scenario, one of the relationships is positive and the other one is negative. So we will take a look at this in more detail with the help of a formula in the upcoming slides. So just remember what the initial relationships between the omitted variable and y is, and the omitted variable and the x is. A formula for the omitted variable bias is as, we'll be looking at that on this slide. So remember that beta 1 hat minus beta 1 can be written like this. So when this is a scenario, what is actually your x minus x bar, which is xi minus mu x and ui. So we're basically looking at the covariance between x and u. So this expectation over here boils down to the covariance of x and u, and if the covariance between x and u is equal to 0, this would mean that this numerator over here is actually equal to 0. So it would simply mean that this whole term will become 0 and mean that the coefficient that we get from the regression analysis, which is beta 1 hat minus the population estimator, will actually be equal to 0, which would mean that both of them are the same, and that is what we are after. We want both of these to be the same, which would mean that the OLS estimator is the blue estimator, which is the best linear unbiased estimator. But if the covariance of X and U is not equal to 0, what does that mean? So what that simply means is that this might be the case of omitted variable bias, because this is one of the conditions for omitted variable bias. It would also mean that the first assumption of OLS will not be satisfied. So just assume a situation that the assumptions number 2 and assumptions number 3 of OLS are being satisfied, but assumption number 1 is not being satisfied. So what will happen in this scenario? So what will happen is that it would simply mean that the covariance between X and U will not actually be 0. It would mean that this fraction will actually be a number. Now this can be a positive number or a negative number depending on how the correlation between X and U is, and it all boils down to, we don't need to actually get into the logistics of how we actually solve for this, but if we solve for this, and this is shown in the appendix of the book, this will give us this fraction over here. Now in this fraction, sigma U is the standard deviation of U, sigma X is the standard deviation of X, and this last coefficient over here is the correlation between X and U. Correlation of X and U. So if assumption number 1 is correct, then the correlation between X and U will be 0. But if the assumption number 1 of OLS is not correct, it would mean that the correlation between X and U will not actually be 0, which would ultimately mean that this will not actually be 0. This whole fraction will not actually be equal to 0, which will mean that beta 1 hat minus beta 1 will not actually be equal to 0. So once again we will get to a situation in which our sample estimator is not actually a good predictor of our population estimator. So we have already established that beta 1 hat is equal to beta 1 plus this fraction over here, and this fraction will not be equal to 0 if the first assumption of the OLS does not hold or is not satisfied. And that will simply be because if the first assumption of the OLS is not satisfied, the correlation between X and U, correlation between the regressor and the residual, will not actually be equal to 0, and if this is not equal to 0, then this whole fraction will not be equal to 0, which will mean that the estimation of beta 1 hat will not be very accurate, because it will not be equal to beta 1 and it will have either an upward bias or a downward bias. So if an omitted variable z is both a determinant of y, meaning it has a relationship with the dependent variable, and it is also correlated with x, meaning the correlation between x and u is not equal to 0, then the OLS estimator beta 1 hat is biased and is not consistent. So let's stick with the example of districts with few ESL students. ESL means English for students of English as a second language. So if there are fewer ESL students in a school district, they will probably do better on standardized tests, and they will also have smaller class sizes, meaning they will have bigger budgets. So ignoring the effect of having many ESL students would actually result in overstating the class size effect. Now, why will that be the case? It will simply be the case because let's look at this correlation coefficient over here, which is the correlation between x and u. So this correlation between the student-teacher ratio and the percentage of ESL students will actually be a positive one. Why will this be positive? Because when there's a higher percentage of ESL students in a school district, they will also have higher student-teacher ratio. On the other side of it, the situation is also pretty much the same. Lower student-teacher ratios will mean higher budgets, and it will also mean lower percentage of ESL students in the school district. So overall, this correlation will have a positive effect because both X and U actually move in the same direction. So if this is a positive number, then this whole fraction will be a positive number, which would mean that we are actually overestimating the population beta 1, because beta 1 hat becomes the population beta 1 plus some positive number. So it would simply mean that we are overestimating. So it simply implies that there will be an upward bias in the estimation. So another way of looking at this would be dividing the sample into different parts, but along two dimensions. So the first dimension would be whether the student-teacher ratio is less than 20 or whether it is greater than equal to 20. The second dimension would be what is the percentage of English learners in the school district. So the first row gives us the data for all the districts combined. But over here, in these rows, the data is for when the percentage of English speakers is less than 1.9%, when it is between 1.9 and 8.8%, when it is between 8.8 and 23%, and when it is above 23%. So you can see the average test scores in all of these school districts for student-teacher ratios less than 20 and greater than 20, and you can also see the difference, meaning this difference is simply the 657.4 minus 650, or in this scenario 644.5 minus 665.4, which is equal to minus 0.9. And you also are given the t statistics for the difference in means test, which is the two sample t-test which we did in the third chapter, I think. So we can see from here that the districts with fewer English learners have higher test scores. So what are the districts with fewer English learners? So this is the row which corresponds to the districts with few English learners. So they have higher test scores. If you look at the student-teacher ratio, it's basically not having a huge impact on the students' test scores. So 64.5 and 65.4 are the average test scores for schools with student-teacher ratio less than 20 and greater than 20 for the districts which have less than 1.9% of English learners. On the other side of it, you can also see that there is a higher number of schools with lower student-teacher ratio than the number of schools with higher student-teacher ratio for the districts with the low number of English learners. So both of these situations tell us that both the conditions of omitted variable bias are actually being met over here. So the first is that the percentage of English learners will have an impact on average test scores, and you can see this when you actually compare this row with the last row. So you can see on average that the average test scores for both low student-teacher ratio and high student-teacher ratio is actually lower than for the districts with low percentage of English learners. So first condition is actually met. So second condition is that the covariance between percentage of English learners and student-teacher ratio is not equal to 0, and that can also be seen because percentage of English learners, when it is low, just like in this category, there are way more number of schools with lower student-teacher ratio than the number of schools with higher student-teacher ratios. But when the percentage of English learners is higher, then you can see that the number of schools with low student-teacher ratios is less than the number of schools with higher student-teacher ratio. So it would mean that the percentage of English learners is also correlated with the student-teacher ratios. So overall, you can also see that for the overall sample, the difference in the means for the districts with higher student-teacher ratio and low student-teacher ratio is a higher number than when we actually divide the sample by the percentage of English learners in school districts. And that is simply showing the case of omitted variable bias, because some of this variation in the overall sample was actually because of the variation in the percentage of English learners in the school districts. Now, causality is very important in regression analysis. So the test score and student-teacher ratio and fraction of English learners example shows us that if an omitted variable satisfies the two conditions for omitted variable bias, then the OLS estimator in the regression omitting that variable is biased and inconsistent, and that is simply because of the correlation which arises between X and U, or in our example, between the student-teacher ratio and the fraction of English learners. Now this raises a deeper question in the sense that how do we define beta 1? Like what precisely do we want to estimate when we run a regression? But before doing that, let's take a look at a couple of other examples which are given in the book for the explanation of omitted variable bias. So what we will be doing is that we will take a look at both of these examples and look at whether both of these examples follow the two conditions for omitted variable bias. So in a sense, we will basically be looking at whether we should include these two variables in our analysis or not. So the first variable is time of day of the test. Now, time of day of the test will probably have some sort of an effect on the test scores of students. But will it have an effect? Will it be correlated with the student-teacher ratio? The answer is no, because time of day of the test has nothing to do with student-teacher ratio, but it has a lot to do with the test scores. So one of the conditions for omitted variable bias is met, but the other one is not met, which means that this is not the case of omitted variable bias. The other example that we will look at is parking lot space per pupil or per student. So what this means is that parking lot space per student will probably be correlated with the student-teacher ratio, because if the student-teacher ratio is higher, there will be less parking space, and if it is lower, it will be more parking space. But will the parking space per student be affected or will have an effect on the test scores? The answer to that is no, because student parking space or parking lot space has no relationship with the test scores of students. So one of the conditions in this scenario is also satisfied for omitted variable bias, while the other one is not, which simply means that this is not the case of omitted variable bias. So getting back to the question that we raised earlier, how do we define beta 1 and what are we actually looking at whenever we are running a regression? So there are a number of ways in which we can take a look at our regression analysis and try to look at what we are actually after. So the first one is we want to estimate the slope of a line through a scatter plot as a simple summary of the data to which we attach no substantive meaning. Now, if that is the case. This really does not, in your data analysis or your regression is not driven by any sort of economic theory. It would simply mean that we cannot really extract any useful information by just imposing a line on a scatter plot. Going back to the example in one of the earlier lectures, like temperatures rising and ice cream sales might actually have a relationship, but if you look at temperature rising and ice cream sales, and actually look at ice cream sales versus the crime rate, then that relationship does not have any economic theory driving it. So even if we stick a scatter plot, stick a line through the scatter plot of the data, it will not have any sort of economic meaning to it. So this sort of analysis can be useful at times, but is not very interesting intellectually. The second way we can describe our regression analysis is that we want to make forecasts, we want to make good predictions for the future, and this can be done through regression analysis, but this is more in the realm of time series forecasting, and we'll probably not be doing this in this course, but we will you guys will come across this concept probably in a higher level econometrics course. Now the third and the most interesting way of looking at the regression analysis is that we want to estimate the causal effect of y on y of a change in x. Now why is this important? It's simply because as policymakers, if you are looking at the relationship between student-teacher ratio and test scores, you want to design some sort of a policy around it. So if the student-teacher ratio actually has a significant and a huge impact on the test scores of students, then you can basically put in money to actually lower the student-teacher ratio. If that is not the case, if our finding says that there is no causal effect of student-teacher ratio on student test scores, then there is no need to put in money. So huge decisions regarding how much money should be funneled into a project, how the taxpayers' money should be used, all of these decisions can actually be made on the basis of regression analysis. And that is why this is the way I want you guys to look at the regression analysis, which simply means that you're trying to estimate the causal effect on y of a change in x. Now what is causality? Causality is a complex concept, and as we move along this book, we will actually see that getting to causality or getting at causality is actually a very, very difficult process, because there are a number of confounders which will always be confounding the relationship between your regressor and the dependent variable. But in order to get at true causality, it can be defined to be the effect measured in an ideal randomized control experiment. So remember the distinction that we made in one of the earlier chapters between randomized control trials and observational studies. So most of what we are dealing with in this chapter deals with the case of observational studies. But if somehow we could run a randomized control trial or a randomized control experiment on the relationship between student-teacher ratio and test scores, that will get us to true causality, because it will not have any biases, it will not have any confounders. We will actually be just measuring the effect of student-teacher ratios on test scores, because everything else will be assigned randomly. So let's take a look at all of these different words which make up the phrase ideal randomized control experiment, and let's look at the significance of each of these. So ideal means subjects all follow the treatment protocol, perfect compliance, no errors in reporting. So you're basically getting at this perfect sort of data collection where everyone is following the guidelines of the experiment and there is no lack of compliance. Randomized, what does that mean? Subjects from the population of interest are randomly assigned to a treatment or control group. So if your control group is that student teacher ratio is greater than 20, then your treatment group can be then the student teacher ratio is less than 20. But what is important is that both of these treatments and controls are assigned randomly, meaning none of your other aspects such as your income, such as the quality of teaching, such as your ability to speak English will have an effect on whether you are assigned the treatment group or the control group. So in this sense, everything else, all the other attributes of the students are randomly assigned, only apart from the one aspect or one attribute, which is whether they get to be in a smaller student-teacher ratio classroom or in a higher student-teacher ratio classroom. Controlled means having a control group permits measuring the differential effect of the treatment. So it simply means that you have a control group and you have a treatment group. So when you actually get the results of the experiment, you can actually measure the differences in the test scores between the treatment group and the control group. An experiment, which is the last word, simply means that subjects have no choice. So there is no reverse causality in which subjects choose the treatment they think will work best. Now compare this sort of an analysis with what you get in an observational study or what you get in real life. So if you are living in a school district, how much choice do you have as far as choosing your student-teacher ratio is concerned? The answer to that is none, because you will actually go to the school which is in your district, and whatever student-teacher ratio they have is what you get. So it simply means that if in your school district there are a lot of students with English as their second language, then it basically means that that sort of treatment is not really assigned randomly, and the student-teacher ratio that the students are choosing is not assigned randomly, because they are basically self-selecting into the school. What that simply means is that they have no choice into the school that they go, and they are going to the school which is the only school available to them, which will simply mean that the student-teacher ratio is not a random allocation or is not randomly assigned. So once again, going back to the same example, imagine an ideal randomized control experiment for measuring the effect on test score of reducing student-teacher ratio. So in that experiment, if suppose we can actually run that experiment, which will again be a very costly experiment, and that is one of the reasons why randomly controlled experiments are hard to do, because the expense is the biggest aspect about it, is the biggest reason for it. So, but let's suppose in a hypothetical situation, if we are actually able to do this experiment, students would be randomly assigned to classes which would have different sizes. Because they are randomly assigned, all student characteristics, meaning all the U's, everything in the U, everything in the residual, would be distributed independently of student-teacher ratio. In a sense, it would mean that the covariance between the student-teacher ratio and U would be equal to 0. Bringing us back to the first assumption of OLS, which shows that the covariance between student-teacher ratio and U should be equal to 0, and in a randomized controlled experiment, that will always be the case, because all the other student characteristics are assigned randomly. But how does our observational data differ from this ideal? So once again, so we are in a situation where the districts in which the schools are located will be serving some sort of a population, and those population will have different characteristics. For example, some populations might be more richer than others, some population might have more percentage of English learners than others. It would simply mean that your student-teacher ratio will actually be correlated with the residual, the U, and it would simply mean that the first assumption of OLS will not be satisfied, and this will result in the case of omitted. This can result in the case of omitted variable bias. Because remember that the other condition for omitted variable bias also has to be fulfilled, that whatever is in the U should have a relationship with the dependent variable. So randomization plus control group means that any differences between the treatment and control groups are random and they are not systematically related to the treatment. On the other hand, in an observational study, characteristics will be systematically related to the treatment. The treatment in this scenario would be student-teacher ratio, and the characteristics which will be systematically related to student-teacher ratio would be variables such as the income of the households which is served by the school, the percentage of English learners in the school, the quality of teachers in the school, the quality of the school infrastructure, including the number of computers available to the school and whatnot. So all of these things will actually be systematically related to the student-teacher ratio, because if you have lower budgets, then you have higher student-teacher ratio, and all the other things that I just pointed out which can be included in the U, in the residual, are also related to the budget that the school will have. So we can pretty much eliminate the difference in percentage of English learners between the large and small treatment groups by examining the effect of class size among districts with the same percentage of English learners. This simply means that if we divide the sample between the different percentages of English learners in the school district, and we actually run regressions for each of those subsamples like it was shown in one of the earlier tables, we can probably get to see the effect of student-teacher ratio on test scores between different subsamples of population, meaning for different subsamples of the different levels of percentage of English learners in the school districts. So that will be one way to control for the effect of percentage of English learners when estimating the effect of student-teacher ratio on test scores. But the ideal situation would be that if we are actually doing a randomized control experiment, that will actually get us to true causality. So let's return to omitted variable bias. So there are three ways to overcome the problem of omitted variable bias. So the first one is run a randomized control experiment, which as I pointed out, it will probably be a very expensive proposition, and also human beings cannot always be experimented on. So that is the least feasible solution in most cases. The solution number two would be adopt the cross-tabulation approach, so with finer gradations of student-teacher ratio and percentage of English learners within each group. So just like the table that I showed earlier, in which the subsamples were along two dimensions, along the dimension of student-teacher ratio and also the percentage of English learners in the school district. And then if you run separate regressions on each of these like subsamples, you will be able to extract the effect of student-teacher ratio on test scores, while also controlling for the percentage of English learners in the school district. Option number three would be user regression, in which the omitted variable, the percentage of English learners, is no longer omitted. It simply add that as one of the other regressors in the regression analysis to get us to a multiple regression analysis, a multivariate regression analysis. When that is done, and option number three is more often than not the most feasible option, because it you don't result, it does not result in a loss of observations like in option number 2, and it's also not expensive to do like option number 1. So consider the case of two regressors. So first of all, my disclaimer for this is that this like adding another regressor changes some things, but the overall concept behind regression still remains the same, as in the case of having only one regressor. So in this situation, when you add the other regressor, which is x2, obviously there will be a coefficient of x2 which will be beta 2, and everything else pretty much remains the same. Y is the dependent variable, x1 and x2 are the two independent variables. Yi, x1i and x2i denote the ith observation on y, x1 and x2. Beta naught is the unknown population intercept. Beta 1 is the effect of y of a change in x1 holding x2 constant. So that is the new part over here. So whenever we are looking at beta 1, it would mean that we are holding x2 constant. Whenever we are looking at beta 2, it would mean that we are holding x1 constant. So essentially we are getting to that condition in economics called ceteris paribus, meaning everything else held constant. So this is the interpretation of coefficients in multiple regression. So this is the equation, the regression equation. So if this is the regression equation and there is no change in x1 or x2, then this is the population regression line. But what is the population regression line after the change in x1? Suppose there is a change in x1 and that change is denoted by this change over here. So this change of x1 is being added to the original level of x1, and that becomes the total x1. If that is the case, this change in x1 will actually result in a change in y, and as you can see over here, x2 is actually held constant. So if that is the situation, it would simply mean that the change in y will actually be equal to beta 1 multiplied by the change in x1. It's a very simple kind of situation. It's pretty much the same situation as before in the case of one regressor. The only change here is that we are holding x2 constant. So beta 1 is still equal to change in y over change in x1, but we are holding x2 constant. And when we are interpreting beta 2, we will interpret it along the same lines. It's equal to delta y over delta x2, meaning change in y over change in x2, holding x1 constant. Beta naught is the predicted value of y when x1 and x2 are both equal to 0. So pretty much everything remains the same. We are just adding one more variable to the analysis. We are interpreting everything else the same as before in the case of one regressor. The only difference is that whenever we are looking at the effect of one regressor on y, the other regressor should be held constant. So what we are trying to do is that we are trying to minimize the sum of least squares. So this is the expression that we are trying to minimize. So remember that yi minus this whole expression over here gives us the residual, and we are trying to minimize the squared sum of residuals, and this will basically be done through a minimization problem using calculus. We don't really need to get into that right now because this is beyond the scope of this lecture. But the software, the statistical software that we'll be using, for example STATA, will actually do this for us. So by using this sort of a minimization problem, we will actually be able to get the estimators of beta naught and beta 1, which we don't need to calculate by hand. So let's suppose we get those coefficients. So remember that in the previous lecture we had only one regressor, which is the student-teacher ratio, and this is the coefficient that we got, minus 2.28. Now suppose that we are also including the percentage of English learners in the classroom. So what happens to the coefficient of student-teacher ratio when we add this new variable percentage of English learners? We see that there's a drastic reduction in the coefficient from when there was only one regressor to now when there are two regressors. And that is simply because the correlation between student-teacher ratio and the percentage of English learners in the classroom is not equal to 0, which means that this was the case of omitted variable bias, which means that some of this variation was actually because of the percentage of English learners in the classroom, and now that we have control for it, and this also is a coefficient which is not equal to 0, it would mean that that variation is taken away from the coefficient of student-teacher ratio, and that's why there is a reduction over here. Now, as I pointed out earlier, we don't really need to calculate the coefficients by hand, but the STATA software that we are using for this course will actually do that for us. So simply just add the variable PCTEL to the existing regression equation, and that will give us the coefficient of PCTEL as well. So you get the coefficient of student-teacher ratio as well as the coefficient of PCTEL as well as your beta naught. So when you get these three coefficients, you can pretty much get the equation of the straight line or equation of the regression line, which basically shows the relationship between student-teacher ratio, percentage of English learners on test scores. So measures of fit for multiple regression are more or less the same, or at least follow the same logic as the measures of fit for regression with only one regressor. So remember that the yi, which is the actual y, is equal to yi hat, which is the predicted y, plus ui hat, which is the residual. So that remains the same as before in the case of single regressor. So what is standard error of regression? That's the standard deviation of your residuals. So that remains the same as before. What is root mean squared error? So that's the standard deviation of your residuals without the degree of freedom correction. So remember that standard error of regression will be with the degrees of freedom correction, meaning we'll be doing n-1 or n-2 or n-k depending on how many degrees of freedom we lose, while root mean squared error is without the degrees of freedom correction. R square is the fraction of variance of y explained by x, so that will remain the same from the analysis when we were using only one regressor. But now we have this new adjusted R square and this one has a degrees of freedom correction, so that adjusts for the estimation uncertainty, and adjusted R square is less than R square, and we'll take a look at all of these in the coming slides. So what is the standard error of regression? That is basically shown by this formula over here. We don't really need to calculate it, as STATA output will give us that. So remember that this takes into account the degrees of freedom correction. So we have n minus k minus 1. K is the number of regressors used in the analysis. If there are only two regressors, then we'll have n minus 2 minus 1. On the other hand, root mean squared error is the same thing, the standard deviation of u, but without the degrees of freedom correction. So it will just have 1 over n instead of 1 over n minus k minus 1. So R square pretty much remains the same from the one regressor analysis, because it's still equal to ESS over TSS, or you can also calculate it by using 1 minus SSR over TSS. So explain sum of squares will be basically how much variation is explained by the regressor from the total variation, and 1 minus SSR over TSS is basically SSR is the explanation because of the U, the residual. So if So whatever the sum of squared residuals is the proportion of the total sum of squared, it would mean that that is the percentage or the fraction which is explained by the residual. So 1 minus that will be what your regressor is actually explaining as far as the variation in y is concerned. So we have already seen in the previous lecture what ESS, SSR and TSS are equal to, so I will not really go into that. But the important point to note over here is that the R square always increases when you add another regressor. And why is that the case? Let's take a look at these equations over here. So when another regressor is added, it simply means that your U, your residual, should actually be explaining less of the total sum of the total variation than before. So because of that, this fraction SSR over TSS will actually become smaller, which means that 1 minus this fraction will actually be a bigger number. So R square will actually increase. You can also take a look at how ESS will change. So if another variable is included in the regression analysis, it would mean that more of the total variation is explained by the regressors. So this fraction will actually increase, which will mean that R square will increase. Now, on the other hand, the adjusted R square corrects this problem, because we don't want researchers or statisticians or economists to always be including variables just so they can increase R square. So the adjusted R square actually corrects that problem by penalizing you for including another regressor. So how does it do that? So it basically adds this fraction to the calculation of adjusted R square. So previously for R square we had 1 minus SSR over TSS. Now for the adjusted R square we have 1 minus this fraction n minus 1 over n minus k minus 1 multiplied by SSR over TSS. So now let's take a look at what the two different things will happen when you add another regressor. So when you add another regressor, this fraction SSR over TSS will actually reduce, and that is simply because the amount of variation explained by the residual will actually fall. So the numerator will be lower than the denominator than before, so this fraction will actually reduce. Now what will happen in this scenario over here for this fraction over here? So n minus 1 will remain the same, but n minus k minus 1, k is the number of regressors. So let's suppose you add another regressor. It would mean that the denominator over here will actually increase, which would mean will actually decrease, sorry. So when the denominator will decrease and the numerator remains the same, it would mean that this fraction will actually increase overall when we add another regressor. So two opposing things are happening when we add the regressor. This fraction will go down in number and this fraction will go up in number. So whichever effect dominates will basically then determine whether adding another regressor increases or decreases your adjusted R square. So for example, if the effect of SSR over TSS dominates, it would mean that R square will actually increase. But if you are being penalized more for adding another regressor, then it would mean that your adjusted R square will actually decrease. But I mean, obviously in the case when n is large, this denominator will basically not be highly influential in affecting this total fraction. So whenever n is large, the two measures, R square and adjusted R square, will be very similar to each other. So let's compare the measures of fit from the single regressor analysis and the multiple regression analysis. When we do that, we see that the R square actually changes from 0.05, which was a very low R square initially, to 0.425. 0.26. So now more of the variation in y is explained by the x variables. The adjusted r square is also pretty much the same. While if you look at the standard error of regression, that actually decreases from 18.6 to 14.5, which is also a good sign, which means that our errors are not as far apart as before, meaning the variance of the errors is not as high as before. So why are the r square and adjusted r square so close in this equation? Is simply because the number of observations is pretty large to have any sort of change on adjusted r square. So now let's take a look at the least squares assumptions for multiple regression. So these also pretty much remain the same as in the case of only one regressor, apart from the fourth assumption which we are going to add over here. So the conditional distribution of u, the first assumption is that the conditional distribution of u given the x's has mean 0. It simply means that the covariance between u and all the x's is actually equal to 0. The second condition of the second assumption of OLS with the multiple regression analysis is that both all the x's and the y variable are independently and identically drawn, and that will always be the case whenever you are randomly drawing a sample. The third assumption is that large outliers are unlikely, so that was the assumption before, and now the assumption remains the same, that all of the x variables and all of the y variables, the kurtosis of all of those is less than infinity, which means that there are no huge outliers. This fourth assumption is a new one, that there is no perfect multicollinearity, and we will explain more of that in the upcoming slides. So assumption number 1 is that the conditional mean of u given the included x's is 0. So pretty much the same interpretation as in the regression with a single regressor. You're basically looking at whether there's a correlation between x and u. If that is the case, then we have one of the conditions for omitted variable bias. And if that is the case, then we should actually include that omitted variable in the regression. So assumption number 2 is that all of the x variables and the y variable are independently and identically drawn, and this is satisfied automatically if the data are collected by simple random sampling. Now obviously when we were discussing this earlier, in time series and panel data this assumption is harder to meet than in observational studies, because in time series the x1 from the previous time period will probably be highly correlated with the x1 in the current time period, and that will be true for all the x's and all the y's as well. Large outliers are rare. Once again, you can simply check this by doing a scatter plot of any data that you have, and that should basically give you an idea whether there are some huge outliers in the data or not. Assumption number 4 is that there is no perfect multicollinearity. What is perfect multicollinearity? It is the case when one of the regressors is an exact linear function of the other regressors. What does that really mean? So let's suppose when you were running this regression between the test scores and student-teacher ratio, by mistake you typed in student-teacher ratio twice. So what the software will try to do in this scenario is that it will try to estimate the effect of this STR while holding this STR constant. Now, can you actually see the effect of a variable while holding it constant? No, you cannot. So what will happen is that STATA will automatically drop the second STR, which was a typo essentially, and to avoid the case of perfect multicollinearity, because in the case of perfect multicollinearity you cannot actually estimate the coefficient of the regressor. So perfect multicollinearity is when one of the regressors is an exact linear function of the other regressors. So just like in the previous regression, if beta 1 is the effect on test score of a unit change in STR holding student-teacher ratio constant, well, obviously that cannot be the case, because if you are moving something, if you are changing something, we cannot also keep it constant at the same time. We'll come back to the examples of perfect and imperfect multicollinearity, but with these four OLS assumptions in hand, we can derive the sampling distribution of beta 1 hat, beta 2 hat, up till the number of regressors that we actually have in the analysis. So under the four least squares assumptions, the sampling distribution of beta 1 hat has mean beta 1. Variance beta 1 hat is inversely proportional to n. So pretty much, we don't really need to get into the distribution of beta 1 hat and beta 2 hat, because it kind of is very complicated. If you are really interested in that, you can take a look at the appendix. But the two important things to consider are that the overall idea remains the same, that we are still following the law of large numbers, and we are also sticking to the central limit theorem. So conceptually there is nothing new here. The sampling distribution of beta 1 hat and beta 2 hat and all the other regressors, all the other coefficients of regressors will pretty much follow the two key properties of law of large numbers and central limit theorem. So once again, coming back to what perfect multicollinearity is, it is when one of the regressors is an exact linear function of the other regressors. So the example from before is that you include student-teacher ratio twice in the regression equation. In that case, the student-teacher ratio is exactly explaining the student-teacher ratio, which was added the second time around. So it will basically give us the case of perfect multicollinearity. So perfect multicollinearity will also be evident in a lot of other cases. So for example, if we regress test score on a constant d and b, where d is equal to 1 if student-teacher ratio is less than 20, and b is equal to 1 if student-teacher ratio is greater than 20. So essentially what we have is that we have two dummy variables. So d will be equal to 1 if the student-teacher ratio is of a lower number, less than 20, and it will be 0 otherwise, and b will be equal to 1 if the student-teacher ratio is high, and it will be 0 otherwise. So in this scenario, b will be equal to 1 minus d. So think about this for a second. So whenever the student-teacher ratio is a high number, it would mean that d will actually be 0, while b will actually be 1. So b will be equal to 1 minus d, meaning 1 minus 0. Alternately, it will also be the case that whenever d is equal to 1, when the student-teacher ratio is small in the classroom, b will be equal to 0. So in this case, bi is equal to 1 minus di, which means that one of the regressors is an exact linear function of the other regressors, and therefore we will get the situation of perfect multicollinearity. Now the book also provides a couple of other interesting examples of perfect multicollinearity. So the first one is that let's suppose we include the percentage of English learners in the classroom as one of the regressors. But we also include the fraction of English learners in the classroom. Now what will be the difference between the percentage of English learners and the fraction of English learners? It will simply be that the percentage will be the fraction of English learners multiplied by 100. So in that case, one of the regressors is once again a linear function of the other regressor, simply meaning that the percentage of English learners will be equal to fraction of English learners multiplied by 100. If that is the case, if we include both the percentage of English learners and the fraction of English learners in the regression analysis, it will be the case of perfect multicollinearity. Another example that the book provides is, let's suppose you are including the percentage of English learners in the regression analysis, but let's suppose you also include the percentage of English speakers in the regression analysis. So in this scenario, what will be the percentage of English learners? It will be equal to 1 minus the percentage of English speakers. Or to be more precise, it will be equal to 100 minus the percentage of English speakers. So in this scenario, if you include both the percentage of English learners and the percentage of English speakers in your regression analysis, one of those variables can actually be an exact linear function of the other variable, which would mean that once again we will get into the case of perfect multicollinearity. So if we look at this example over here of D and B as our variables which we are including, where B is equal to 1 minus D, so would there be perfect multicollinearity if the intercept were excluded from this regression? Now that's an interesting question. So if that is the case, if the regression, if the intercept was excluded from this regression, then there will not be a case of multicollinearity, because you can think of the intercept as a variable which always takes the value of 1. And when you do that, you will basically get the coefficient of that variable which is equal to the intercept from the regression analysis. So if that is the case, if essentially the estimation of the intercept is like estimating the coefficient of a variable which always takes the value of 1, then it would mean that B plus D equals to 1. 1 will be the variable which always takes the value of 1 will not be equal to B plus D, because there will not be any variable which always takes the value of 1 if we actually exclude the intercept, and it would mean that the problem of perfect multicollinearity will actually be avoided in this case. So next thing that we'll do is the dummy variable trap. So the example that we went over in the last slide, which is basically like, will excluding the intercept solve the problem of perfect multicollinearity? So this situation is actually called the dummy variable trap. So what this simply means is that suppose you have a set of multiple binary or dummy variables which are mutually exclusive and exhaustive. So for example, if you are controlling for whether the student is freshman, sophomore, junior, or senior, and you actually have separate variables for freshman, sophomore, junior, and senior, in which if you are in one of those categories, then you take the value of 1. If you are not in that category, you take the value of 0. Then it would simply mean that freshman plus sophomore plus junior plus senior will actually give us the value of 1. So this is called the dummy variable trap. So how do we resolve this issue of perfect multicollinearity? We can simply, since the linear expression freshman plus sophomore plus junior plus senior will be equal to 1, which is essentially equal to the variable which always takes the value of 1, and the estimation of that variable will actually give us the intercept, or the beta naught. So it simply means that you have two solutions to this dummy variable trap. The first solution is that you can omit one of the groups from the analysis, meaning for example, if you omit the seniors from the analysis, it would mean that freshmen plus sophomores plus juniors will not actually be equal to 1 anymore, because you have taken out one of the dummy variables which was previously included, or you can simply omit the intercept, which always which can be considered a variable which always takes the value of 1. So doing one of the two things will actually resolve this issue of dummy variable trap and will resolve the issue of perfect multicollinearity. What are the implications of using these solutions? So if you omit one of the groups, you can basically you will not be able to estimate the effect of being a senior on test scores, for example. But if you omit the intercept, you will not be able to see the level of your regression line, essentially. So more often than not, I will actually go with the first option rather than the second option, because the intercept, as much as the interpretation of the intercept might not actually make much sense, but it's still important to include it, because it basically gives us the level of the line of best fit. So perfect collinearity usually reflects a mistake in the definitions of the regressors or an oddity in the data. And like, for example, you can include the same variable twice, or you can include two different variables which pretty much mean the same thing, like the percentage of English learners and the fraction of English learners, or the percentage of English learners and the percentage of English speakers. If you have perfect multicollinearity, your statistical software, STATA in our case, will either crash or it will drop one of the variables arbitrarily. So in that case, you basically have to go back and look at your list of regressors and see like which variables have been dropped and why have they been dropped, and what was the case of perfect multicollinearity because of which one of the variables has been dropped. Now, we have so far looked at the case of perfect multicollinearity, but you can also look at find cases of imperfect multicollinearity. So what does that mean? So it simply means that if two regressors are very highly correlated, then their scatter plot will pretty much look like a straight line, which would mean that they are collinear. But unless the correlation is exactly +1 or -1, that collinearity is imperfect. So what might be an example of imperfect multicollinearity? So an example might be that if you are including the percentage of English speakers, percentage of English learners in your regression analysis, and you are also including the percentage of immigrant families in the regression analysis when you are looking at the effect of these two on test scores. Now, if you look at the economic theory between the relationship between these two, which is deriving the relationship between these two variables, usually if there is a higher percentage of families which are immigrant families, it will also mean that there is a higher percentage of English learners in the school district. So in this scenario, one of these variables will not exactly be a linear function of the other, but both of these will still be highly correlated. So it will not be the case of perfect multicollinearity, but this will still be the case of imperfect multicollinearity. So how do we check that? So we have a number of different ways in which we can actually find measures of multicollinearity between our X variables. The most common way is the variance inflation factor. The command for that is VIF in STATA, and you can simply just put that command VIF and add in all of your X variables to actually see what the correlations or how much multicollinearity is actually there between all of your X variables. But as long as there is no perfect multicollinearity, STATA will still estimate the coefficients of all of your X variables, and imperfect multicollinearity becomes an issue that you have to think about as a researcher, because you want to you want to actually find the coefficients which make the most sense rather than just including variables without thinking about whether they make sense or not in your regression analysis. So once again, imperfect multicollinearity implies that one or more of the regression coefficients will be imprecisely estimated, and that is simply because the idea is that the coefficient on x1 is the effect of x1 holding x2 constant, but if that is not happening, if x1 and x2 are highly correlated, it would mean that when you're looking at the coefficient of x1, x2 is not constant. So the variance of the OLS estimator of the coefficient on x1 will actually be large, which would mean that this will not be the estimator with the lowest variance, which once again violates the assumptions of OLS. So imperfect multicollinearity results in large standard errors, and that has consequences for the OLS coefficients. So this is what we have for this lecture. So in the next lecture, we will actually take a look at the hypothesis testing and confidence intervals with multiple regressors. Until then, take care. I hope you had fun listening to this lecture and it helped you in basically looking at linear regression with multiple regressors. Take care. Goodbye.